Before dawn returns to longer views. I like to think of 3 Atlas as a quiet guest passing the porch light. It moves on a course that will not close, a clean arc that tells us it came from beyond our sun and will keep going. No alarms, no rush, just a steady crossing through the inner neighbourhoods where we can watch it for a while. From Earth, the distance stays comfortable. So our role is simple: look carefully, compare notes, and let the story unfold at the object's own pace. I picture the thin path of a hyperbola laid over a calm sky chart. A single curve carried by gravity and time. Mars orbiters take a turn at the window from their side of the yard. Hubble traces the light-impatient exposures. JWST listens for faint chemistry where sunlight touches ancient ice. Closer to home, survey telescopes keep the beat, marking small changes in position and brightness, fixing the rhythm of the visit. The pattern is familiar: warm the ice. Watch the glow, chart the change. A soft sunward plume has appeared in some views, like a pale ribbon that points back toward the light. It's the kind of feature that invites you to breathe and settle, because it behaves the way dust and ice usually do when a long cold surface meets gentle heat. If you hold a second image in mind, make it a slim timeline discovery in midsummer, a near sun swing in late season, and an early winter return to easier mornings when the glare moves aside. There are a few quiet facts worth carrying into this walk. This is the 3rd confirmed interstellar object we've seen, and its open path fits the bill. Its approach stays safely far from Earth, so our attention can rest on what it's made of and how it changes. Early spectra suggest that carbon dioxide is strong compared with water at the distances sampled so far, and that both ice and vapour are present together. None of this asks for drama. It asks for patience and clean measurements, because patience is the thread. Agencies plan their looks like waypoints on a map. Mars orbiters peered across a broad span of space to catch the coma from a different angle. Hubble gathered high-resolution images that show a sun-facing haze more than a crisp tail, which is exactly what you'd expect when grains and gas spill outward in sunlight. JWST, tuned to faint fingerprints, added texture hints of water ice, a breath of water vapour, and other volatiles that appear when the surface warms. Each piece sits beside the others without strain. You might wonder, as people do, whether a visitor like this could be a crafted thing rather than a natural one. It's a human question, and it comes from a good place: curiosity about our place in a wider community. Observations so far point to ordinary comet physics: a nucleus that's small compared with its glowing shroud, no measurable push beyond gravity, and chemistry that follows the heat. That picture doesn't close the door on wonder. It gives us a steady floor to stand on while we look. There's comfort in the geometry. 2. From Earth, the object slid into a patch of sky too close to the sun for a while, and then it will come back out, ready for another round of careful watching. That pause isn't a missing page. It's a built-in intermission that lets heat sink a little deeper and gives the gases time to tell us which layers are stirring. When it returns to wider angles, we'll compare what we saw before with what we see after, and the differences will help us read the surface like a slow, clear clock. I'll move slowly with you through the evidence, step by step, and keep the language calm and plain. When a number helps, I'll use one and no more. When a picture helps, I'll paint it with concrete lines, a plume pointing sunward, a curve that does not close, a timeline that marks when certain instruments could see best. Together those scenes make a map you can hold in your head without effort. The point is not to chase a headline, but to rest with a real object doing what such objects do under light. If this pace feels right, stay with me for the chapters ahead. Chapter 1, A Visitor from Between the Stars. Tonight you're safe and unhurried while we consider a small visitor gliding far away through the sun's quiet reach. Think of a calm sky where most paths are loops that close, and then imagine one path that does not. Observation suggests this object follows a hyperbolic track, the graceful curve of something that came from outside the family of planets, and will continue outward when its pass is done. It is the 3rd confirmed interstellar object we have seen, and it behaves in the simple, steady way that unbound travellers usually do. It does not wander near our world. It does not ask us for worry. It offers us a chance to watch and learn at an easy pace. From the start, agencies and observatories treated it like what it is: a rare but natural opportunity. It's likely that the distance remains comfortably large for the entire encounter, so the work becomes one of careful seeing. Hubble takes long looks that resolve a haze around a compact centre. JWST listens for faint signatures of gases and cold grains as sunlight wakes the surface. Mars orbiters, from their vantage, add a different angle on the same scene. Ground surveys keep the beat of its motion, noting small shifts against the stars and gentle changes in brightness as warmth and geometry evolve. You can hold two quiet anchor images in your mind as we begin. The first is simple, a thin hyperbolic curve sketched across a clean star chart, a path that enters and leaves without closing. The second is a soft sunward plume, a pale feather of dust that points toward the light. Those two images, path and plume, frame almost everything that follows. They suggest origin and behavior without noise. They invite patience. Patience matters because interstellar visitors are slow conversations. We see them under different lighting, from different angles, and with different instruments that emphasize different things. One instrument might map a distribution of gas where carbon dioxide is strong compared with water at this stage. Another might catch glints from icy grains drifting away from the nucleus. Observations suggest a volatile rich surface is responding to sunlight in expected ways, and that simple physics can explain the glow we record. Each dataset supports the next without strain. The way a series of calm notes builds a melody you recognize. It helps to remember what outgassing means in ordinary terms. Ice near the surface warms, a little vapor escapes, and small grains of dust and ice lift away into the light. The nucleus remains compact while the surrounding cloud carries most of what we see. It's likely that much of the brightness we notice is not the center itself but the dust and gas that reflect and scatter sunlight around it. That's why photographs show a softened halo rather than a crisp, geometric outline. The Comet is the story more than the core is. Distance, too, is a quiet part of the story, even when a visitor like this is at its nearest to Earth. The gap stays wide by everyday measures. That is why the tone of the observing campaign is steady rather than urgent. Schedules are set, exposures are planned, and the object is traced across weeks as viewing geometry changes. Observations suggest the window around the Sun will briefly limit what we can see from Earth, and then the geometry opens again when glare moves aside. That pause is not a loss. It is another way the object tells us who it is, because heating during that intermission can change what rises from the surface next. You might feel a tug toward the big question, could a thing like this ever be made rather than grown by nature? It is fair to ask, and it is kind to answer gently. The best evidence we have points toward a natural comet, with a compact nucleus that is small compared with its shroud, with gas and dust responding to sunlight, and with motion governed by gravity. It's likely that if any unusual features appear, they can still sit within the wide range of dust and ice behavior we have seen in other comets. That answer does not close doors, it simply keeps our feet on steady ground while the data arrive. The quiet strength of this encounter is the variety of eyes watching. Hubble's images give shape to the sunward haze. JWST's spectra sketch out what the gases are, and how they shift with distance from the Sun. Mars orbiters add a cross-check from a very different angle, catching the same coma in a different light. This diversity is how careful science works when the subject is faint and far. Each instrument brings a fresh piece to the same modest puzzle, and together they reduce the chance that a single impression will mislead us. The timeline itself is a comfort, a discovery in warm months, a near-sun passage in late season from our point of view, and then a return to cleaner mornings when the angle improves again. Each phase sets a different kind of question. Before the glare, the questions are about awakening what sublimates first, what grains fly, how the coma grows. During the glare, the questions turn inward to modelling and anticipation. After the glare, the questions are about change. Did the balance of gases shift? Did any structure sharpen? Did the coma thin or thicken in a way that points to subsurface layers warming? Everything about this object encourages a calm pace. The distance is large. The motion is smooth. The signals are faint but measurable with the instruments we have. Observations suggest that carbon dioxide is prominent early, and that water in both ice and vapor states is present too. It's likely that we are seeing layers near the surface respond first, with deeper ice lagging as heat moves inward. All of that fits a familiar pattern for cold bodies waking in sunlight, if you wish. You can imagine the observing effort as a map with waypoints. Not a chase. Each point adds a small clarity. None requires triumph or shock. The path does not close. The plume points toward the light. The chemistry matches what a volatile rich traveller would show. These are calm statements with room for nuance as measurements refine. They let us remain curious without leaning toward worry or spectacle. And because the mood here is unhurried, we will take the same approach in the chapters that follow. We'll start with what early images reveal about size and outline, and why a small solid centre can appear wrapped in a much larger glow. From there, we'll follow the track it travels across the sky, and see how geometry shapes what the instruments can learn. Step by step, the picture will sharpen, and you'll have an easy frame for each new detail. For now, carry the 2 anchor images with you, a path that does not close, and a sunward plume that points to warmth doing what warmth does. With those in mind, we can move to the first close looks and explore how size, light, and texture begin to tell us who this traveller is. Chapter 2, First Close Looks, Size and Shape, Gently Sketched. We'll move gently now, letting the first close images set the pace as we outline size and shape. Early pictures do a simple thing very well. They show that most of the light we see is not the compact centre but the cloud around it. Observation suggests that a small nucleus hides within a bright, diffuse coma, which is exactly what you would expect as sunlight wakens volatile material near the surface. The glow is soft rather than sharp because grains and gas scatter light in many directions, blurring the boundary between object and space. This is not a flaw in the view, it is the view we need, because it tells us that active, natural processes are underway. Hubble's role in this phase is quiet and essential. It resolves the coma with enough clarity to show a sunward enhancement, a subtle thickening of the haze toward the light. That enhancement is the pale ribbon many images share, and it helps fix our mental picture of where energy is flowing. It's likely that heat arriving from the sun frees molecules from the surface and loft small particles outward, and those particles then reflect sunlight back to us. The plume is not a jet with rigid edges. It is a soft gradient that reveals how the coma breathes. The nucleus itself remains modest by all signs we can safely trust at this stage. Because the coma dominates the light, any estimate of the solid body demands caution. Observation suggests the nucleus is far smaller than the visible cloud, small enough that its glow is overwhelmed by the halo of dust and gas it releases. This is a common experience with active comets. When ice lifts away and grains take flight, the shroud becomes the subject, and the centre stays veiled inside its own exhalations. Scale can be tricky here, so we will handle it with care. The images let us bracket the nucleus within sensible bounds without pretending we see a crisp edge. It's likely that the solid piece is compact in absolute terms while the coma extends far beyond, growing and thinning with distance from the sun. This contrast between a small core and a wide, glowing envelope is not a contradiction. It is how light behaves when countless tiny particles scatter it, and how gas disperses when it escapes into space without strong confinement. Texture matters as much as size. Some comets throw narrow features or fan-like structures, but early looks here emphasize smoothness more than dramatic shapes. That smoothness pairs with the sunward enhancement to suggest gentle, widespread release rather than a handful of dominant vents. Observation suggests that the distribution of active areas, if it is uneven, still adds up to something balanced on the whole. A balanced pattern helps explain why the motion stays governed by gravity alone, because pushes from different directions can cancel when averaged over time. The colour of light and the fingerprints of certain gases add a second layer to these first looks. Instruments sensitive to faint signatures find carbon dioxide abundant at this stage compared with water. It's likely that water appears in both ice and vapour forms, alongside other trace species that thermally awaken under sunlight. None of these results require rare chemistry. They reflect a body rich in familiar volatiles warming in a predictable way, where the easiest to free molecules lead the show while deeper or less mobile reservoirs lag. When you look again at the sunward plume through this lens, it becomes even easier to read. Warmth favours the side facing the light, and that side lifts more material. The plume points back toward its source not because anything mechanical is steering it, but because gas and dust respond to the direction of heating. The density drops as you follow the light away from the centre, and the path you trace with your eyes is a gradient in both brightness and particle concentration. Observation suggests that the plume's shape fits this natural pattern without strain. It can be tempting to ask for a clean silhouette of the nucleus, a single frame that shows a solid edge and shuts the door on guesswork. Nature rarely grants that with active objects. The very processes that let us detect them with ease, outgassing and dust release, also obscure their cause. It's likely that the best way to constrain the centre is by pairing images like Hubble's with spectra, and with careful tracking of the object's motion over time. Each method gives a different handle on size and mass, and together they weave a stronger net than any single image could. As the object moves along its unclosed path, lighting and geometry will continue to change. The distance from the Sun shifts the balance of gases. The distance from Earth changes the scale of what we can resolve. The angle between Sun, object, and observer refines which portions of the coma we see most clearly. Observations suggest that these shifts will offer new chances to infer particle sizes, scattering behavior, and the distribution of active patches on the surface. First looks are just that first, and they set a baseline for everything that follows. Through it all, the lesson stays gentle. A small solid center can produce a large, luminous presence when sunlight frees even a modest amount of material. A plume can look like a ribbon without implying any rigid structure. A smooth coma can hide countless small sources of activity that add together in a balanced way. It's likely that later chapters in the story will adjust details, tighten bounds, and reveal fresh subtleties, but the foundation we've laid here is steady. It matches what cold, volatile rich bodies do under light. In the next chapter, we will follow the track this traveller takes across the sky and see how speed, geometry, and vantage point shape what our instruments can learn. Chapter 3, The Path It Travels Speed and Geometry. We'll keep a gentle pace as we follow its path across the sky, safely distant and steady in its motion. Begin with something simple you can picture without effort. The object moves on a curve that does not close. That single idea removes any sense of hurry. It comes from outside the Sun's usual family and will continue on when this brief passage is over. The shape of that curve is ruled by gravity alone to a very good approximation. Observations suggest the trajectory fits a clean hyperbolic solution without a measurable push from outgassing strong enough to bend its path beyond the pull of the Sun. That is a calm sentence to carry, because it tells us we're watching a traveller guided by ordinary celestial mechanics. The stage on which this plays out is broad, but the geometry is kind. From our vantage on Earth, the object's track sweeps through the inner system in a way that keeps it far from us. Distance is not a vague comfort here. It is the everyday reality of the encounter. That large gap gives observers time to plan, to measure, and to watch how viewing angles change the details we can read. It's likely that the motion appears retrograde against the background of stars, meaning it seems to drift in the opposite direction of most planets, and that apparent reversal adds a distinct flavour to its sky dance. None of this changes what it is. It only changes how we see it. Geometry sets what instruments can do at each moment. When the line from the Sun to the object and onto Earth becomes too straight, glare from the Sun blocks our view. That interval is not a problem to be fixed. It is a planned intermission in a long, quiet performance. Before that break, ground surveys track positions and brightness as the object brightens modestly under increasing warmth. Space telescopes gather spectra and images that chip away at the unknowns. What gases appear first, how dust behaves, whether any narrow features emerge. After the break, the sky opens again, and the same questions can be asked with the added power of comparison. What changed? What stayed the same? What does that say about layers just below the surface? Speed enters the story, but not as a source of drama. An interstellar visitor carries the imprint of a long journey. The way its velocity projects onto our sky and onto its path around the Sun is part of the signature that tells astronomers it is unbound. The numbers can be quoted when needed, but for restful purposes you only need to know this. The motion is fast enough to mark it as a traveller from elsewhere, yet entirely in line with what gravity demands for such an arrival. Observation suggests that its speed at great distance aligns with the range expected for objects born around other stars and nudged free by time and chance. Another element of geometry is the plane of the ecliptic, the reference sheet that holds most planetary motion. The object's path slices that plane at a gentle angle, not so steep that it becomes exotic, but distinct enough that we can tell its story with simple pictures, a curve entering from one side, crossing the Sun's realm, and leaving through another door. It's likely that this near-ecliptic orientation is one reason so many assets can contribute. The line of sight from Mars, from Earth, and even from other spacecraft becomes favourable at staggered times, and each vantage offers a complementary piece. Space agencies planned those looks as waypoints, not as rescues. The aim is to create a continuous record with alternating perspectives. Astrometry, the precise measurement of position, does the quiet heavy lifting. When observatories across the world and in space submit their timed positions, analysts fit those dots to a path and study the tiny deviations from a purely gravitational arc. Observation suggests those residuals are small and consistent with no strong extra force. That absence of a measurable push tells us two things. First, the object behaves like a natural comet whose emerging gases are either modest in total effect or arranged in a way that cancels their tugs over time. Second, the mass we infer does not have to be extraordinary to account for the data we have. Neither of these points asks us to relax our curiosity. They simply help us frame it. Light matters, not only as brightness, but as angle. The phase angle, the angle between the sun, the object, and the observer changes the look of any dusty envelope. At small phase angles, the coma can seem smoother and more forward scattering, while at larger angles, fans and tails may stand out, because the geometry evolves across the season. We are granted a natural sweep through those angles. It's likely that the apparent shape and texture of the envelope will change in ways that are more about viewing than about the object itself. That is why it helps to think of the path not only as a position in space, but as a sequence of lighting states. Another gentle piece of the puzzle is rotation. Most small bodies spin, and that spin modulates the pattern of activity on their surfaces. We don't need an exact period here to make a calm point if active regions are uneven. Then the coma can breathe with that rhythm. Observations suggest the overall effect so far is balanced rather than wildly asymmetric. That fits well with the finding that motion remains governed by gravity, because a strongly lopsided jet would tend to nudge the trajectory in a way we could detect. Instead, we see consistency with little net push. Vantage points add texture. From the vicinity of Mars, orbiters view the coma across a long line of sight, sampling different depths than we can from Earth. Later, another spacecraft in a different neighborhood may glimpse the traveler at a fresh phase angle. It's likely that these varied perspectives will help separate properties of the grains themselves from the tricks of lighting and projection. When a feature persists across angles and distances, it becomes more securely part of the object's nature. When it fades or reverses with geometry, we know to look for explanations in scattering and alignment. There is a quiet beauty in the way all of this fits together. A traveler arrives, unbound and safe. Geometry sets a schedule that sometimes favors Earth, sometimes favors another platform, and sometimes favors patience while the sun occupies the line of sight. Observation suggests that the path, the speed, and the changing angles all align with what you'd expect from a natural, volatile rich body passing inward and back out again. It's likely that the sharpest pictures of structure will come at moments when the phase angle emphasizes dust features, while the richest spectra arrive when thermal contrasts are strongest. That interplay is not an accident. It is the logic of the sky. Hold one more image as we close this chapter, a simple map with a dotted curve, a few labelled waypoints, and a shaded region near the sun where Earth-based views pause. That map is not a chase plan. It is a reading plan. We turn the page when geometry allows. We underline changes when they appear, and we accept quiet when glare insists. The path tells us where to look next, and the changing light tells us what to expect when we do. With the stage set by motion and angles, we can now listen for what the light itself contains. In the next chapter, we'll let the spectra speak, and see how the balance of gases and ice reveals a chemistry that feels both familiar and intriguing. Chapter 4, What the Spectra Whisper, CO2 Rich and Active. We'll take this slowly and let the light tell its story. Knowing the object remains far away and well behaved, spectroscopy is the art of turning faint glow into meaning. Spread the light into its colours, and certain fingerprints appear narrow bands where molecules absorb or emit. The first round of careful looks at this visitor reveals a theme. Observation suggests the coma is rich in carbon dioxide compared with water at the distances sampled so far, with water present in both icy grains and vapour. That pattern is not a verdict. It is a starting point that reflects where warmth reaches first and which molecules respond most readily. When sunlight meets a volatile rich surface, the easiest to freeze species often steps forward, while deeper reservoirs wait their turn. Two independent lines of evidence make this picture persuasive. It's likely that high-sensitivity space-based spectra detect clear signatures of carbon dioxide along with contributions from water, carbon monoxide, and a trace sulfur-bearing species sometimes found in comets. Meanwhile, wide-field infrared measurements resolve an extended envelope of carbon dioxide gas, showing that this is not a tiny patch of activity but a broad, persistent release. When separate instruments agree on both composition and scale, confidence grows that we are seeing the object as it is rather than as a single method would have us imagine. Think of the coma as a living record of energy flow. Sunlight warms the surface, and volatile molecules begin to escape. Some water arrives as vapour, some as ice grains that drift and slowly sublimate. Carbon dioxide, more ready to leave at colder temperatures than water, can dominate the early scene. Observations suggest this is exactly what we're catching, a blend where carbon dioxide leads, with water present enough to be heard but not yet carrying the chorus. That balance may evolve with time and distance, because heat sinks deeper and awakens layers that were insulated during the first passage through stronger sunlight. Texture reappears, now supported by composition. A smooth coma in imaging pairs naturally with a broad carbon dioxide envelope in spectroscopy. It's likely that the absence of strong, narrow jets in the early surveys reflects a distribution of active patches that is either widespread or balanced. When many small vents contribute, their flows overlap and blur into a soft glow. That kind of release fits the chemistry we see and explains why the apparent motion stays governed by gravity alone. Any small pushes from escaping gases tend to cancel at large scale. The spectra also hint at the grains themselves. Ice leaves its mark not only as vapour but as subtle absorption features that tell us something about particle size and state. Observations suggest that water ice is present among the grains, consistent with a coma that scatters light while slowly changing as ice transforms to gas. A body showing these signatures is doing the ordinary work of a comet warming, releasing and rebalancing as it moves through sunlight. That ordinariness is the point. It quiets the more imaginative leaps without denying wonder. We are still witnessing the chemistry of an object from another stellar neighbourhood. We are just placing it on familiar ground. Carbon monoxide offers a second thread. In some comets, it becomes prominent at very large distances. In others, it remains a minor player. Here, early results lean toward carbon dioxide and water carrying the day. With carbon monoxide present but not commanding the scene, it's likely that the relative strengths we measure will shift as the object passes its closest approach to the Sun, and then cools again. What matters for now is that the recipe makes sense: a volatile that frees early, a major reservoir that wakes later, and smaller contributors that trace particular temperature regimes. One virtue of a coordinated campaign is the ability to cross-check. The same molecule can be sensed in different ways, directly in high-resolution spectra, and indirectly in broad imaging that maps where gas glows in aggregate. Observations suggest the carbon dioxide envelope extends far beyond the immediate neighbourhood of the nucleus, a sign that production is sustained rather than spiky. It's likely that this extension will change with time, thinning or thickening as heat penetrates and as the surface adjusts. Those changes will help us decide whether the activity comes from a few persistent regions or from wider swaths that respond as daylight swings around a rotating body. Spectra can also flag trace species that add nuance. A modest detection of a sulfur-containing molecule, for example, sits comfortably within the known chemistry of comets, and is consistent with material that formed in a cold environment where such compounds can survive. None of these details points to anything engineered. They point to a place of origin where certain ices were abundant, and to a journey during which radiation and micrometeoroid gardening may have altered the outermost layers. The balance we see now is a conversation between that initial recipe and the recent heating cycle. There is a patience built into this kind of listening. When geometry drives us into a brief pause, the spectra we already have become a baseline. After the pause, new spectra will test whether water takes a larger role, whether carbon dioxide holds its lead, and whether the grain signatures sharpen or fade. Observations suggest that these before and after comparisons are the surest way to read layers. The surface shouts first, the subsurface murmurs later, and together they form a slow duet that tells us how porous, how crusted, and how mixed the near-surface zones are. For a human-scale understanding, you don't need every line in the spectrum. Hold a small handful of truths. It's likely that carbon dioxide currently dominates the gas we see, that water exists as both ice and vapour, and that the coma's smoothness reflects many contributors rather than a few dramatic jets. Independent instruments agree on these points, which is why the tone in agency updates remains measured. They are not hiding excitement. They are describing a body that behaves in the way physics says it should. If you imagine a single picture to anchor all this, let it be a gentle one, a diffuse envelope glowing softly, with a slightly brighter side facing the sun, and within that glow the quiet signatures of carbon dioxide and water weaving through the light. That image will carry you through the next rounds of data without strain. The notes may rise or fall, but the melody will still be sunlight meeting ice and releasing familiar molecules into space. This chapter leaves us with an expectation rather than a cliffhanger. As the object continues on its unclosed path, the balance of gases may evolve, and the shallow patterns of scattering may change in step. In the next chapter, we'll shift from what is in the light to how the light is scattered, and let grains, angles, and a subtle sunward feature add texture to the story. Chapter 5, Light, Dust, and the sunward feature will keep our attention soft and steady while the light does the talking. Far from any need to hurry when you look at the object as a painter would, starting with broad tones and then adding detail. The first tone is the glow itself. The coma is a diffuse envelope that scatters sunlight in all directions, and within that glow the side facing the sun is a little brighter. Observations suggest a smooth, sunward enhancement rather than a sharply carved tail, the kind of gradient that forms when countless fine grains and a breath of gas flow together. That gentle thickening is our first clue that heat is the sculptor here, working in familiar ways on ice-rich material. The second tone comes from how light is polarized after scattering from those grains. Polarization is a quiet property, but it carries information about size, texture, and composition. Observations suggest an unusually deep negative polarization branch at small phase angles, a feature that means the light is slightly more aligned in a direction opposite to what you might expect. In human terms, it tells us the grains could be coated with frost, or built from aggregates that favor backscattering in a distinctive way. It reads as odd only until you remember that comets are factories of subtlety, where particle histories and surface coatings change the way light returns to us. A third tone is the near absence of rigid structure. Early wide-field images found a coma that looked calm rather than striped by narrow jets. It's likely that many small sources across the surface contribute simultaneously, their flows overlapping into a soft halo. That overlap matters. If only a few strong vents dominated, we would expect sharper features, shifting patterns, and perhaps a small push on the trajectory. Instead, we see a balanced release and a path that continues to follow gravity with little sign of extra force. Now we can knit those tones into a picture of the sunward feature that some observers highlighted. A light, forward-facing brightening is visible in certain geometries, and it can mimic a short, sunward antitail at specific times. The word can conjure drama, but the physics underneath is content to stay simple. Grain size and survival time control where the brightness peaks. Grains that sublimate slowly can travel a bit before they fade. Grains that sublimate quickly leave their strongest mark close to the source. As the viewing angle changes, so does the balance of forward and back-scattered light, and the sunward enhancement can emerge without any need for special equipment on the object itself. Here is a careful what-if you can hold lightly. What if the sunward feature arises from uneven survival times of sublimating ice grains, with larger grains lingering while smaller ones disappear sooner near the heat source? Even if that is true, it lives entirely within the ordinary behavior of sunlight and ice, not within the realm of craft or intention. That immediate reassurance matters, because it keeps the conversation grounded while we leave room for details to settle. Dust physics closes the loop between appearance and cause. Coatings of water ice, mixed with more volatile ingredients like carbon dioxide, can create composite grains whose optical behavior is not a simple average of their parts. Observations suggest that water ice is present among the grains, and that gas phase signatures of common volatiles are also present. It's likely that these ingredients set the scene for the deep negative polarization rough, icy aggregates tending to backscatter light and to align the electric field of that light in a way our instruments can detect. Nothing in that chain implies anything more than cold material waking under soft heat. Another quiet player is the phase angle, the sun-object observer angle that shapes how the coma presents itself. At small phase angles, forward scattering can brighten the region near the sun-facing side. At larger angles, the brightness can shift and spread, emphasizing different zones of the halo. This is why the same object can look subtly different across days even when nothing fundamental has changed. It's likely that portions of the apparent anti-tail are variations of this lighting geometry, layered on top of the grain survival times and outflow speeds that set the raw supply of scattering particles. Grain size distributions evolve with time as well. When the object first warms, fragile aggregates can break apart, creating a surplus of smaller particles that scatter light efficiently. As activity continues, the mixture can tilt toward grains with coatings that resist quick sublimation. Observations suggest that the coma's texture is smooth enough to imply many contributors, rather than a few dominant vents. That smoothness naturally blends these grain populations together, yielding a brightness profile that is gentle in every direction and only slightly stronger toward the Sun. It helps to pause here and place this in the wider family of comet behavior. Negative polarization branches are not unheard of. They appear in surveys of dust-rich comas with certain grain properties. Sunward enhancements are also common when illumination and viewing geometry line up to favor forward scattering. It's likely that the combination we see here feels unusual because the object itself is unusual in origin, not because the physics is path-breaking. Interstellar provenance simply adds a layer of narrative interest. While the light tells a familiar story about ice, dust, and warmth, if you're picturing the scene, let it be calm. A rounded glow, a modest brightening toward the Sun, and within that glow, tiny grains carrying frost and trapped gases. The brightening is not a spear or a beam. It is a gradual increase shaped by where grains survive and where they vanish. The polarimetric signal does not demand a special engine. It points to texture and coating, to aggregates and frost. Observation suggests that this reading is consistent with the spectra that highlight carbon dioxide early, and water in both grain and vapor form. The pieces fit without strain. Rotation can add a soft rhythm to this display. As the body turns, active patches take their turn in sunlight, and local plumes shift. When many small patches are involved, the net effect is a mostly steady halo with minor ripples rather than a strongly pulsing fan. It's likely that any rotational modulation is present but muted, woven into the smooth brightness we see instead of standing apart as a strobe. That, too, supports the idea that the outflow is balanced, which in turn sits well with the finding that the path remains overwhelmingly gravitational. You could ask whether unseen structure might be hiding beneath this apparent smoothness. The honest answer is that small, narrow jets can hide when they are weak, when the viewing angle blends them into the global haze, or when exposure times average them out. Yet the large-scale signals do not require them. Observation suggests that the bulk of the light is carried by a broad distribution of particles, and that any fine features, if present, are passengers rather than drivers of what we measure at scale. The comfort here is that every layer of evidence leans in the same direction. Imaging points to a sunward enhancement consistent with forward scattering and ongoing release. Polarization points to icy, possibly aggregate grains that favor backscattering in a way that deepens the negative branch at small phase angles. Spectra point to a mix of volatiles that explains why the coma is active and why the balance may shift with time. It's likely that continued observations from different angles will polish this picture rather than upend it. Hold one restrained image as we close a soft ribbon of brightness leaning toward the Sun. Not sharp, not insistent, just a quiet mark of where warmth flows. That is enough to carry you into the next question, where brightness and texture meet motion. In the following chapter, we will weigh how all this activity shows up, if at all, in the trajectory itself, and why the path still reads as gravity's handwriting. Chapter 6. The Quiet of the Trajectory Non-Gravitational Limits. We'll keep a calm watch while we ask whether an outgassing gives any measurable nudge to the path, knowing the object remains comfortably distant. Astrometry is the art of letting small differences speak. Observatory teams record where the object appears against the stars at carefully timed moments. Analysts then compare those positions to the path a purely gravitational traveller would follow and look for patterns in the tiny differences. Observation suggests those residuals are small and consistent with an orbit that does not show a statistically significant push from outgassing. That sentence carries more comfort than it may seem. It tells us the path is clean, the fit is good, and the object is behaving like a natural body whose internal processes are not strong enough or not asymmetric enough to change its course in a way we can currently measure. This is where physics and patience meet. A comet's escaping gases can, in principle, act like tiny thrusters, nudging the nucleus along or away from its nominal track. To matter at the scale of an orbit fit, the push has to persist in one direction, or at least average to something other than zero. It's likely that in this case the outgassing, while real, is either modest or balanced. Balanced can mean several things. It can mean many small vents spread across the surface, whose tugs cancel over a full rotation. It can mean seasonal effects that rise and fall in a way that evens out across the weeks of data. The important part is that the sky does not show a sustained deviation from the path gravity writes. There is a careful inference we can draw from this quiet. If activity is present and all signs say it is yet, the orbit does not show a measurable shove. Then either the nucleus carries enough mass to shrug off small impulses, or the impulses are arranged in a near-symmetric pattern that nets out. Observation suggests the latter is plausible given the coma's smoothness and the absence of dominant jets. It's likely that both act together a reasonable mass and a widely distributed set of active regions that smooths the effect. Here is a gentle what-if you can tuck beside that inference. What if multiple vents on different parts of the surface produce forces that cancel so effectively that the net non-gravitational signal disappears into the background noise of measurement? Even if that is the case, it points to symmetry in natural venting, not to any special mechanism or design. The reassurance belongs next to the question, because the same images and spectra that reveal activity also reveal balance. It's worth noting how the geometry of observation matters in this assessment. Non-gravitational effects are easier to confirm when you can track the object for long arcs under different lighting conditions. The brief interval when the sun's glare closes, Earth-based views is a pause that limits the continuous record, yet we do not return from that pause empty-handed. The pre-pause orbit fit becomes a baseline. Post-pause measurements extend the arc. Observations suggest that such stitching improves the sensitivity to tiny accelerations, because any real push would bend the extension away from the baseline in a consistent fashion. It's likely that as more data arrive after reappearance, the limits will tighten further and the picture will sharpen. Numbers are tempting here, but restful comprehension does not need them. All you need to hold is that the absence of a strong non-gravitational term is a result, not a lack. It means the models that follow a sun-only pull explain the data well. That outcome aligns with everything we've learned about the coma so far: smooth texture, sunward enhancement without rigid jets, and a volatile mix that looks vigorous yet broadly distributed. It sits comfortably beside the finding that spectra agree across instruments on the leading role of carbon dioxide early on, and the presence of water in both grain and vapor form. Another quiet support comes from the apparent consistency of brightness changes with solar heating rather than with mechanical or engineered rhythms. When natural illumination drives activity, we expect activity to rise with warmth, to carry a rotational ripple if the surface is uneven, and to respond to local sunrise and sunset on the nucleus. Observation suggests that the changes we do see can be described within this framework. It's likely that as the object rotates, minor shifts in the coma's thickness and the location of the sunward brightening occur, but they do not combine into a sustained shove. Skeptical questions are welcome here, and they can be answered without hurry. Could an unknown mass distribution complicate the interpretation? It could, but mass distribution affects spin, state, and mechanical stability more than it would produce a clean, persistent acceleration along the orbit. Could unrecognized jets be hiding, pointed in a way that our cameras rarely catch? They could, yet the global pattern, the smoothness, the polarization, the broad carbon dioxide envelope speaks of many contributors rather than one or two dominating sources. It's likely that any hidden jets are fine structure riding on a wider flow, and their pushes cancel as the body turns. Even the possibility of short-lived bursts fits within the calm picture. A brief episode of enhanced activity might create a small, temporary deviation that later data absorb as the fit updates. Observation suggests there is no enduring trend that demands a permanent non-gravitational term. That is how the absence of a signal accumulates into knowledge. Each additional night without a consistent shove strengthens the conclusion that gravity alone is enough to explain the path we trace. None of this erases curiosity about origin or history. A trajectory free of measurable extra push tells you about the present behavior. It does not speak over the questions of where the object formed or how its surface evolved during interstellar travel. Those questions belong to composition, texture, and kinematics, which we explore in other chapters. Here, the message is modest and firm. The path is quiet. It maps cleanly onto a gravitational arc. It accommodates the activity we see without requiring exotic mass or a hidden engine. As a listener, you can rest in that modesty. The sky does not whisper everything at once. It gives you brightness, then polarization, then spectra, then motion, each offering a hint of the whole. Observation suggests the hints align. It's likely that post-reappearance tracking will either keep confirming the gravitational picture or reveal a tiny, balanced non-gravitational term that stays within the range of ordinary comet physics. Either outcome is calm, either helps us refine mass, spin, and venting patterns. Hold one last thought as we close this chapter. The absence of a measurable shove is not the absence of character. It is the character of a natural traveller whose many small breaths average to stillness in the grander motion. That character sets the stage for how claims and counterclaims should be weighed. In the next chapter, we'll look at how ideas ranging from the conventional to the speculative fit or fail to fit within the quiet facts we've gathered so far. Chapter 7, Claims, Counterclaims, and the Centre of Gravity. You can relax into this part, because the object keeps its distance and its behaviour stays steady under patient eyes. Curiosity rushes ahead of certainty, and that's natural. A bold claim can arrive overnight, while careful measurements take their time. In this case, a few voices have suggested that the visitor might be crafted rather than natural. The suggestion makes headlines because it's dramatic, but the sky does not answer to headlines. Observations suggest a simpler picture, a compact nucleus wrapped in a broad coma, outgassing that follows sunlight, and a path that matches gravity without a measurable extra shove. That is not a dismissal of imagination. It is a placement of imagination on a firm floor. Let's define what counts as persuasive. When multiple, independent instruments converge on the same reading, confidence grows. When the same behaviour appears at different angles and at different times, confidence grows again. It's likely that the weight of evidence here rests on exactly that kind of convergence imaging, spectroscopy, polarization, and precise tracking that tell a coherent story. None of these tools needs the others to work, yet they point in the same direction. Start with the light you can see. Images show a rounded glow with a subtle brightening toward the sun, a gentle thickening rather than sharp jets. That look matches dust and gas lifting from a small body warmed on one side. Polarization results add texture, an unusually deep negative branch at small phase angles that hints at icy, possibly aggregated grains. Observations suggest this combination fits within known dust physics, where grain size, frost coatings, and clumping shape the way light scatters. Neither the glow nor the polarization requires anything more exotic than sunlight working on cold, porous material. Now consider motion. Astrometric fits compare timed positions to the curve a gravity-only path would trace. Observations suggest the residuals, the small differences, stay within the range you expect when no persistent push is present. That does not mean outgassing is absent. It means any tugs from escaping gases are modest or balanced. It's likely that many small sources across the surface contribute in a way that averages out over a rotation, leaving the large-scale path unchanged to our sensitivity so far. If an engineered propulsion were acting, it would need to mimic a subtle, symmetric pattern across days and weeks. That imitation is possible in fiction. It is not required by the data we have. Composition brings a second anchor. Spectra indicate a coma where carbon dioxide is strong compared with water at the distances sampled. With water present as both ice and vapour, observations suggest an extended envelope of carbon dioxide, implying sustained release rather than briefer. Narrow bursts, these are the signatures of a volatile rich surface waking under light. It's likely that as heat sinks inward, the balance will shift and water will take a larger role, which is a familiar evolution in active comets. None of this asks for technology. It asks for patience as layers warm. What, then, of anomalies? The deep polarization feature is unusual, and a sunward enhancement can be called an anti-tail in certain views. Those words can sound like red flags until you translate them. Grain properties and viewing geometry can deepen the negative branch of polarization at small phase angles. Forward scattering and survival times can brighten the sun-facing side. Observations suggest that these effects vary with angle and distance in predictable ways. A single oddity might tempt speculation. A pattern that aligns with known scattering physics does not. Mass estimates deserve a calm word. 2. People sometimes convert no measurable non-gravitational term into it must be very massive. That leap is larger than the data support. It's likely that symmetry and venting can hide a small push without demanding an extraordinary mass. In other words, a balanced set of small breaths can leave the grand emotion unchanged. When models combine photometry, activity, and dynamics to bracket size and mass, the uncertainties are broad at first and tighten with time. That is how the record improves without drama. There's also the human part of science to acknowledge. Extraordinary claims do not threaten careful work. They invite it to do what it always does: gather, compare, and test. Peer review and replication do not crush ideas. They keep ideas honest. Observations suggest a consensus forming around a natural interpretation, because that is where the independent lines of evidence point today. It's likely that as more data arrive from different angles and times, what feels tentative will settle, and the object will look even more ordinary in the best sense of that word. If you want a checklist for what would shift the balance toward a non-natural reading, you can make one without strain. Coherent accelerations that do not align with solar heating would matter. Narrow, repeating spectral lines inconsistent with known volatiles would matter. A light curve locked to an artificial duty cycle rather than to rotation and sunlight would matter. Observations suggest none of these signatures has appeared. That absence is not an argument from silence. It is the presence of a consistent natural story across methods. There's room for wonder even when the answer is calm. The visitor likely formed around another star, carried a recipe set by a different disk, and travelled for a long time through the spaces between systems. Radiation and micrometeoroids may have processed its outer layers and tuned its early activity towards certain volatiles. Those are remarkable facts that do not need a technological layer to be interesting. They are part of a wider, patient view of how small bodies move and change across the galaxy. Skepticism goes both ways. We should be ready to change our minds if new, high-quality evidence appears. We should also be ready to let go of dramatic possibilities when the simplest, best-supported explanation keeps winning the tests. Observation suggests that the simplest explanation is holding sunlight warms a compact, volatile-rich nucleus. Dust and gas lift away. The coma glows. The path follows gravity. It's likely that future refinements will decorate this picture rather than overturn it. Hold a modest image as this chapter ends a stack of quiet plots from different instruments, each pointing to the same centre. No one plot shouts. Together they speak clearly. That centre is where we stand while we explore origin, not a place we have to defend. With the balance of claims in view, we can now ask where the traveller may have begun its long journey, and how its motion and chemistry hint at a birthplace beyond our sun. Chapter 8, Where It May Be From, Kinematics to Provenance. Settle in. The object remains a safe, distant study while we trace its likely origins with unhurried care. A path can be a clue to a birthplace. The visitor's track through the inner system follows a curve that does not close, and its motion against the stars reads as retrograde from our point of view. Observation suggests the speed far from the sun is in the range expected for small bodies that were nudge-free from other systems and later wandered near ours. It's likely that the orbit lies near the plane where most planets move, cutting across at a gentle angle that helps multiple observatories take turns. None of these facts alone names a home, but together they define the kind of traveller we are meeting. To ask about provenance, astronomers compare the inbound motion with the local flow of stars and gas. If you think of the galaxy as a set of overlapping populations, thick disk, and halo each has characteristic motions and dispersions. Some analyses have noted that the visitor's incoming velocity may align more closely with the broad, older thick disk population than with the younger thin disk. That suggestion is not a verdict. It is a statistical nudge. Observation suggests that the current kinematic fit allows more than one family, and that measurement uncertainties and past gravitational nudges can blur the trail. It's likely that further tracking will tighten the vectors and clarify how strong that association really is. Here is a careful what-if to hold with a soft grip. What if the object does hail from the galaxy's thick disk, making it very old and shaped by a stellar neighbourhood with different patterns of radiation and chemistry? Even if that holds, the behaviour we see CO2-rich outgassing early, water present as ice and vapour, a balanced coma, a gravity-dominated path stays entirely within natural comet physics. The reassurance sits right beside the idea, so curiosity can breathe without leaning into drama. Kinematics are only half the path to provenance. The other half is chemistry. Early spectra show carbon dioxide strong compared with water at the distances sampled. With water in both grain and vapour forms and smaller contributions from other familiar species, that recipe can arise in more than one way. One possibility is that the body formed in a part of its birth disk where carbon dioxide condensed efficiently, while water remained trapped deeper or released less readily at the temperatures we're seeing now. Another possibility is that a low permeability crust allows carbon dioxide to escape more freely than water at first, temporarily skewing the mix. Observations suggest both interpretations can sit within the data. It's likely that post-conjunction spectra, when warmth has penetrated further, will help distinguish between them by showing whether water strengthens relative to carbon dioxide. Radiation processing adds a slow burn modifier to any origin story. Over a long cruise between stars, outer layers can darken, crust, and trap gases in micropores. That processing can tilt early activity toward the more volatile species while leaving deeper water ice to awaken later. Observations suggest that water ice is indeed present among the grains, which fits a picture where some material is lofted in solid form and then transforms as it drifts. It's likely that the balance of gases will evolve as heat works inward, and the evolution will carry hints about layering and porosity that trace back to formation conditions. The direction in the sky from which the object arrived, the radiant, can be compared with known streams or stellar associations. In this case, the radiant does not point neatly to a single, compact group. That's not surprising. Interstellar objects are expected to come from many sources, their original system signatures erased by countless small tugs and long timescales. Observations suggest the motion fits an unbound visitor with velocities common to older stellar populations. It's likely that provenance will remain a probability statement rather than a named address, which is a normal outcome for such travellers. What would strengthen a particular origin claim? Better kinematic precision from a longer arc of tracking would help, because it sharpens the inbound velocity vector before the sun's pull bends it. More spectra across different distances would help, because they would show how the chemical balance responds to changing heat, revealing whether a crust is throttling water or whether the bulk inventory truly favours carbon dioxide. Observations suggest that both kinds of data are on the way as geometry improves after the bright interval near the sun. It's likely that the combined record will narrow the range of plausible formation environments, even if it never picks a single star. The idea of great age deserves one more gentle pass. If the traveller is thick disk by origin, it may have formed when the galaxy's star formation was more vigorous than now. That history could leave a different ratio of ices or a different texture in the outer layers. None of that changes the present reading of the Comet and the path. It's likely that any age imprint is a second-order effect compared with the first-order rule that sunlight wakes the easiest volatiles first. Age is a flavour in the story, not a new law of behaviour. Provenance is ultimately a meeting point of motion and matter. Motion tells us how the object arrived and how long it will linger. Matter tells us what is leaving the surface and how that mix shifts with warmth. Observations suggest harmony between these two lines, a natural path that needs no extra force, and a natural chemistry that needs no special mechanism. It's likely that we will refine both with fresh looks from different vantage points, including platforms around Mars and a spacecraft farther out that can view the Comet at angles Earth cannot reach right now. None of this closes the door on pleasant surprises. A subtle change in polarization with distance could reveal evolving grain sizes. A late rise in water could map to layers that were insulated early on. A tiny, balanced non-gravitational term might appear once the post-conjunction arc grows long enough to measure it cleanly. Observations suggest that these developments would enrich the natural story rather than overturn it. They would help us read the layering and the venting patterns more precisely, the way a careful sketch becomes a finished drawing. Hold a modest image as this chapter ends a simple vector pointing inward from afar, bending gracefully around the sun, and carrying with it a blend of gases that makes sense for cold material meeting light. That image is enough to support our next step, where fresh vantage points offer new angles on the same traveller. In the following chapter, we will watch how Mars-side views and a distant spacecraft's perspective add depth to the portrait without changing its calm expression. Chapter 9, New Eyes on an Old Traveller, Mars and Distant Angles. We'll take this part gently. The object stays far, and our task is simply to watch from more than one angle. You and I have already seen how a rounded glow can hide a compact centre, and how a soft brightening toward the sun can rise from ordinary scattering. Now the story widens to include views that do not come from Earth at all. Observations suggest that orbiters around Mars planned looks timed to the object's pass across their patch of sky, adding a long, slanting line of sight through the Comet. It's likely that a farther out spacecraft also had windows where the phase angle, the angle between sun, object, and observer, became especially revealing. These viewpoints are not replacements for Earth-based data. They are gentle complements that let us see the same traveller under different light. A change in vantage point is more than a new picture. When Mars looks sideways through the Comet, the line of sight passes through different layers than a view from Earth. That longer column can strengthen faint gas signatures and emphasize how dust is distributed with distance from the nucleus. It's likely that such slanted looks are sensitive to grains that linger, grains that drift, and grains that fade quickly. If you think of the Comet as a breathing envelope, a Mars-side view listens from a different room, catching tones that a front row seat might miss. The phase angle matters here as much as the location of the observer. Small phase angles can deepen the impression of a smooth, forward scattering halo. Larger angles can tease out structure, especially if some grains are big enough to survive a while before they sublimate. Observations suggest that the object's geometry offered both kinds of angles during this season, spread across Earth, Mars, and a spacecraft keeping its own pace farther out. The same grains should not look identical under these changing lights. And that is exactly the point. When a feature grows stronger at one angle and softer at another, physics explains it before speculation arrives. Cross-calibration is a quiet benefit of this arrangement. Earth-based telescopes measure brightness and polarimetry under one geometry. A spacecraft measures similar quantities under another. It's likely that the teams will compare those sets to check whether the deep negative polarization seen at small phase angles softens when the angle grows. If it does, that favours interpretations tied to grain properties rather than to any fixed structure. And if a sunward enhancement persists across angles in the way forward scattering predicts, the case for ordinary dust behaviour becomes even more comfortable. Consider how gas and dust respond to different eyes. Infrared instruments are tuned to the glow and fingerprints of molecules such as carbon dioxide and water vapour. Visible light images see the sunlight that dust reflects. Observations suggest a broad carbon dioxide envelope extends well beyond the nucleus, and that water is present both as vapour and as icy grains. It's likely that the Mars side look, with its long slant through the coma, enhances the sensitivity to that extended gas. Meanwhile, a more distant spacecraft, watching at a larger phase angle, can highlight the edges of the dust distribution as the scattering geometry changes. The result is not two separate stories. It is one story told in two dialects. Rotation threads through this, but gently. As the nucleus turns, active areas come into sunlight and then slip back into shade. From Earth, the rhythm might appear as small shifts in the brightness pattern of the coma. From Mars, the same rhythm plays through a different filter, because the Sun-object observer angle is different. It's likely that the combination helps untangle whether a subtle change is due to spin, to geometry, or to a blend of both. When patterns line up across platforms after adjusting for angle, we learn which parts belong to the object and which belong to the viewing. Even the absence of sharp features is instructive when multiple vantage points agree. If neither Earth's view nor Mars's view shows dominant jets, that agreement raises our confidence that the coma is genuinely smooth rather than smoothed by exposure time or perspective. Observations suggest a balanced release with many contributors rather than a few spear-like fans. It's likely that this balance is the same reason the orbit fit remains almost perfectly gravitational. Many small breaths that cancel, not one strong breath that shoves. There is a human rhythm to the cadence. 2. Teams working from different places share calibration stars, timing standards, and reduction methods so that the data can sit side by side without friction. When spectra gathered under one geometry echo, the main points of spectra gathered under another carbon dioxide strong early. Water present in ice and vapour confidence rises another step. Observations suggest that such agreement is already forming. It's likely that the late-season additions will make the trend clearer rather than stranger. The value of new angles extends to the sunward feature itself. A Mars-side look may catch the enhancement under a phase angle that shifts the balance of forward and back scattering. If the brightening leans as predicted by grain physics, the result becomes a test pass rather than a puzzle posed. If a farther-out spacecraft sees the enhancement fade when the angle grows, that, too, supports an ordinary cause. In both cases, the feature stops being a headline and becomes another checkmark on a list expected under certain light, softer under another, never demanding a special explanation. These combined views also prepare us for comparison after the bright interval near the Sun. A map of before angles and before compositions gives us a baseline. Later, when the object emerges into easier mornings, Earth's view can be laid over those earlier plots to see what changed. It's likely that water's role will strengthen as heat reaches deeper layers, and the cross-platform data will help separate real changes in the object from the tricks of geometry. One last detail is easy to overlook and pleasant to carry. Mars is not just another camera. It is another illumination geometry woven into our shared sky. When its orbit places it in a helpful position, it can see the same coma we see, but with the sunlight hitting from a slightly different direction. Observations suggest that those windows were used in a coordinated way, building a record that emphasizes complement over competition. It's likely that the overall portrait will look more consistent because of this, not less. since the physics that explains one angle must explain them all. Hold a modest picture as we close 3 sketches of the same glow. One from Earth, one from Mars, one from a farther spacecraft. The edges differ a little because the light falls differently, but the heart of the glow is the same. That sameness is the point. With these angles in hand, we're ready for the brief pause imposed by the sun's glare and the calm return that follows. In the next chapter, we'll step through that intermission and the plans for seeing the traveller again when the line of sight clears. Chapter 10 through the glare, conjunction and reappearance. We'll move slowly here, trusting the pause near the sun as part of the plan and not a cause for worry. Every orbit that passes near the sun from our point of view comes with a period when glare overwhelms the view. The object does not vanish. It simply slips into a region of sky that telescopes avoid because scattered light erases faint detail. Observations suggest that Earth-based looks paused around the time it approached its nearest distance to the sun, and teams use that interval to refine models, coordinate schedules, and prepare fresh instruments for the next round. It's likely that the pause is brief in practical terms, a matter of weeks rather than seasons, and that the story continues smoothly when the angle opens again. During this intermission, the object is not dormant. Sunlight keeps working, and heat keeps moving inward through porous layers. The coma does what comas do, it breathes, and its mix evolves as different ices respond. Observations suggest carbon dioxide has led the early scene. With water present as ice and vapour, it's likely that after the pause, water's voice may grow stronger as deeper layers warm and release their stored molecules. That expectation is not a prediction of drama. It is the gentle anticipation that comes from understanding how temperature fronts sink into cold material. The geometry of reappearance is a comfort all its own. When the angle between sun, object, and Earth grows again, the field clears. Dawn or dusk windows present the object at safe separations from the sun, and observatories resume their cadence. Observations suggest that mission plans already include this phase imaging to check morphology, polarimetry to test whether the deep negative branch shifts with new angles, and spectra to compare the balance of carbon dioxide and water before and after the bright interval. It's likely that the most useful reappearance data are the ones that mirror the earlier looks, so that differences can be placed side by side without complication. Astrometry returns to the foreground during this phase. A clean pre-pause orbit solution becomes the baseline. After reappearance, each new position either hugs that curve or asks gently for an update. Observations suggest that the path so far has matched gravity to within tight limits. It's likely that further tracking will lock the solution even more firmly, or reveal a very small, balanced term consistent with natural venting. Either outcome is restful, both keep the traveller in the realm of ordinary comet physics. The coma's texture is also poised to teach us something during reappearance. If water contributes more, grain populations may shift. Fresh frost can coat grains differently. Sublimation fronts can move. The size distribution can tilt toward particles that scatter light in new ways. Observations suggest that the earlier smoothness came from many contributors rather than a few dominant jets. It's likely that pattern will persist, but the brightness profile might broaden, or the sunward enhancement might change subtly as the scattering properties evolve. These are the kinds of changes that instruments are built to measure, with filters and exposures tuned to catch quiet differences. Planning matters here, and it is done with a very human patience. Teams prioritize repeatability over novelty. They try to take the same kinds of spectra at the same kinds of distances and angles, so that comparisons are cleaned. Observations suggest that independent platforms will share calibration standards to keep small systematics in check. It's likely that this rehearsal of methods makes the reappearance feel less like a second act and more like a continuation of the same song. Now played in a slightly different key, safety remains an easy note to sound. The distance from Earth stays large. The path remains unbound. The object is a visitor, not a threat. That steadiness lets the rest of the questions become purely scientific. Did the extended envelope of carbon dioxide shrink or hold as water rose? Did the polarization curve soften as grain sizes shifted? Did any narrow features emerge long enough to stand above the smooth halo? Observations suggest that even modest changes will sharpen our reading of layering, porosity, and thermal pathways under the surface. It can help to imagine the pause and the return as a tide, not a cliff. Light washes over the object, recedes from our line of sight, and returns with a slightly different angle. In that return, the very same aspects we studied before are set out again for examination. It's likely that the greatest clarity will come not from a single dramatic frame, but from the overlay of plots before and after. Same instrument, same filters, same geometry where possible. Science advances most quietly when like is compared with like, and the differences are allowed to be small. One practical gift of the reappearance is time to test specific ideas. If earlier models suggested that a low permeability crust throttles water, the new spectra can look for that throttle opening as heat sinks deeper. If polarimetry hinted at large, icy aggregates, new phase angles can check whether that reading persists. Observations suggest that hypotheses about the sunward brightening forward scattering, grain survival times, and geometry can be checked again under a slightly different light. It's likely that these tests will turn suspected patterns into established ones. All of this unfolds without the need to stretch for meaning. The visitor does not become more or less itself because Earth's line of sight clears. It simply becomes easier to measure again. The grace here is in patience. The coma keeps breathing. The path keeps bending the way gravity writes it, and our instruments keep harvesting the same quiet facts under a new sky. Observations suggest that the tools are ready, the schedules are lined up, and the community is primed to stitch the pre-pause and post-pause tapestries into one. Carry one restful image out of this chapter: a dawn sky with the glow set a comfortable distance from the sun. The air calm, the instruments humming at familiar settings. That's where we pick up the thread, ready to let new measurements refine what we already know. In the next chapter, warmth and depth take the lead as we ask how chemistry evolves when heat has had a little more time to do its careful work. Chapter 11. When warmth sinks deeper. Chemistry that changes. We'll keep the pace slow and easy while the object remains far away, letting the light tell us what has quietly shifted. When we last listened to its spectrum, the theme was clear. Observations suggest that carbon dioxide led the early scene, with water present as both icy grains and a soft breath of vapour. That balance makes sense for a surface waking at a comfortable distance from the sun. Carbon dioxide stirs more readily in that cool regime, while water often waits until heat works a little deeper. The pause near the sun from our viewpoint did not halt the physics. It only paused our line of sight. Beneath that bright interval, sunlight kept drifting inward through pores and cracks, and the near-surface layers kept changing at their own unhurried pace. Think of heat not as a flame, but as a travelling front. It drifts into the topmost layers, loosening gases that were trapped in tiny pockets, and it softens crusts that slowed their escape. Observations suggest that a wide, resolved envelope of carbon dioxide extended well beyond the compact centre before the pause, and that the coma's glow remained smooth rather than striped by narrow jets. Those two facts work together. A broad reservoir was feeding a broad release, and many small sources added up to the soft halo we saw. As the thermal front moves a little further inward, it's likely that water will take a larger role in the gas mix, not in a burst, but as a gentle shift in what the light carries. This is where patience becomes a method. The best way to hear change is to repeat what worked before. Schedules for reappearance lean on the same instrument settings, the same filters, and the same styles of analysis used earlier. That way, the comparison makes itself. If water rises relative to carbon dioxide, the new spectra will show it with the same yardstick. If the dust-to-gas balance tilts as different ices wake, the same cameras will record the new texture. It's likely that a few added phase angles will help, because a change in grain sizes or coatings can alter how the coma scatters light at different angles to the sun. Here is a gentle what-if to hold lightly. What if the December and early season spectra show water strengthening as heat reaches deeper layers that were insulated before? Even if that happens, it would be the expected response of porous ice under sunlight, not a sign of anything engineered. The reassurance belongs immediately beside the idea, so the thought stays curious rather than anxious. A deeper role for water can touch more than chemistry. Grains carry frost, and frost changes how light is scattered. If water rises, we may see subtle shifts in polarization, or a slightly broader sunward brightening, not because anything new was added by design, but because the population of grains has evolved. Observations suggest that earlier polarimetry found an unusually deep negative branch at small phase angles. That signal points towards certain grain textures and coatings. It's likely that if water coatings become more common, the shape of that branch will soften at some angles. The coma can keep its overall smoothness while letting us sense a change in the grains that make the glow. We should also give a calm look to the idea of a crust that holds water back. Some small bodies grow a low permeability layer over time, As radiation and repeated heating sink into the outermost grains, such a layer can throttle water more than carbon dioxide, at least at first. If the crust warms and loosens, water's share can rise without any change in the body's deeper recipe. Observations suggest the early balance could be explained either by genuine abundance or by temporary gating. Reappearance gives us a way to test without strain, because a real inventory difference behaves differently from a temporary throttle as the season progresses. Astrometry plays a supportive role throughout this phase. The orbit fit before the pause acts as a quiet ruler. After reappearance, positions measured against the stars extend that ruler forward in time. If activity changes the gas balance and the dust pattern, any net push on the nucleus could, in principle, change as well. Observations suggest that the pre-pause arc did not require a persistent non-gravitational term. It's likely that even if water rises, the net effect will remain balanced, either because multiple vents cancel or because the total impulse is modest. In other words, chemistry can shift while the path stays almost perfectly gravitational. Dust-to-gas ratios can help tie these threads together. A coma dominated by small, bright grains produces a different look from one with larger, frostier particles that sublimate slowly. If water's role grows, that ratio may change in recognizable ways. The sunward enhancement could broaden or grow softer at the edges if larger icy grains survive longer before they fade. Observations suggest earlier wide-field imaging emphasized smoothness and a forward-leaning brightening that fit the expected geometry. It's likely that the same pattern will remain, with only gentle adjustments in profile as the grain mix evolves. The strength of the campaign now is continuity. Independent platforms have been speaking the same language across the story-shared calibration, common target lists, and repeatable sequences that let small differences rise above background quirks. If water signature deepens, it will deepen in matched spectra. If the polarization curve shifts, the shift will appear in plots that echo the earlier ones. Observations suggest that the more carefully the teams mirror their own earlier work, the clearer the comparison becomes. The goal is not novelty, but clarity. None of this asks for a cliff. The traveller will not flip personalities. It will remain a small, distant body warmed by light, releasing familiar molecules in patterns that match what physics says should happen. It's likely that the most satisfying changes will be modest, a stronger waterline here, a softening of a polarization dip there, a slightly thicker sunward haze under a similar angle. Those are the changes that let us read through the coma to the layers below, and to the pathways that link them. As you listen, keep the earlier anchors handy. Carbon dioxide led early. Water appeared as both grain and vapor. The coma was smooth. The path stayed gravitational. Those anchors will not move. They make room for the new lines to settle where they belong. When we line up the before and after pages, the story should read as one continuous paragraph written in 2 seasons, not as a pair of separate scenes. Carry that ease forward. In the next chapter, we'll let the grains themselves do more of the talking, using scattered light and polarization to show how texture, seas, and coating write their quiet signatures across the glow. Chapter 12, Grains. And the shape of scattered light. We'll stay unhurried here, listening for the small signals that dusty grains and thin frost leave on the light. Scattered light is a patient teacher. It doesn't shout, it nudges. When sunlight hits a dusty coma, it bounces and bends in ways that depend on grain size, shape, and coating. Observations suggest that this visitor shows an unusually deep negative polarization branch at small phase angles, a sign that the light is aligning in a direction that tells us the grains favor backscattering in a distinctive way. That depth sounds dramatic, but it sits comfortably within comet dust physics once you consider icy aggregates, rough surfaces, and the way fine particles clump and frost over time. Imaging sets the stage for that interpretation. We do not see a forest of narrow jets carving sharp fans across the sky. We see a smooth halo with a gentle brightening toward the sun. It's likely that many small sources across the surface contribute simultaneously, their flows blending into a single glow. The blending matters because it means the polarization we measure is an average over a wide population of grains, not a snapshot of a single plume with unusual properties. If the average still comes up with a deep negative branch at small phase angles, the simplest reading is that the grains themselves carry coatings and textures that favor it. Polarization can feel abstract, so it helps to translate. Imagine holding a piece of frosted glass up to the light. The way it softens and skews the beam tells you something about what is on its surface. Comet grains do something similar at a much smaller scale. Coatings of water ice, stirred with a little carbon dioxide and other familiar volatiles, can create aggregate particles whose surfaces are rough and whose interiors are a patchwork of pores. Observations suggest that water ice is present among the grains, and that carbon dioxide and water vapour share the gas space around them. It's likely that this recipe, combined with grain-to-grain clumping, is enough to explain the polarization curve without reaching beyond natural causes. Here is a small what-if to set beside that reading. What if large, slowly sublimating icy grains dominate the scattering at certain angles, driving the deep negative branch and the subtle shapes we see in the Comet's brightness? Even if that is the case, it lives entirely within comet dust models, not outside them. The reassurance pairs with the idea, keeping the discussion grounded while we let the details settle with more data. Phase angle is the quiet steering wheel of all these effects. At small phase angles, forward scattering can brighten the sun-facing side while the polarization dips into that negative branch. As the angle grows, the balance shifts, structure softens or sharpens, and the curve can rise towards zero or beyond. Observations suggest that views from Earth, from Mars, and from a farther spacecraft sample different angles during the season. It's likely that the depth of the negative branch will ease when the angle increases, and that easing will be another mark that grain physics, not exotic hardware, is responsible for the signals we read. Grain-size distributions evolve under light. Fragile clumps can fracture, feeding the coma with smaller particles that scatter efficiently. Coarser, icy grains can persist longer, carrying frost that changes the way they reflect and polarize light. The coma's smooth look tells us that no single family of grains dominates with a theatrical flourish. Instead, families overlap. Observations suggest that the dust continuum contributes much of the visible brightness, which pairs well with spectra that find gases flowing at the same time. It's likely that as water warms into a larger roll, ice coatings will freshen and then thin, subtly shifting the polarization curve's shape across the reappearance window. We can even use the sunward brightening as a check on these ideas. If forward scattering and grain survival times are the real drivers, then the brightening should map smoothly to the direction of sunlight, and it should change predictably as the phase angle changes. Observations suggest that earlier images fit that pattern are modest, forward-leaning enhancement rather than a rigid spear. It's likely that new angles after reappearance will preserve the same behaviour, with only minor adjustments as grain populations evolve. That consistency keeps the explanation comfortably inside ordinary dust and light. Polarimetry across wavelengths adds a second dimension. Different sizes and coatings push the polarization curve in different ways at different colours. A set of measurements at more than one colour can separate families of grains whose signatures overlap at a single colour. Observations suggest that such multi-band work is planned or underway, precisely to turn a good hint into a firm reading. It's likely that the results will sketch out a mixture where icy aggregates and finer fragments share the field. With the aggregates doing more of the work at the angles that deepen the negative branch, rotation can add rhythmic nuance without changing the core picture. If certain surface patches run a little more active, then as the body turns, the coma might lean a little one way and then the other. In a smooth glow, that lean shows up as a barely perceptible change in the brightness gradient rather than as a sharp swing. Observation suggests that any such modulation remains modest, which agrees with the finding that the orbit solution does not require a persistent non-gravitational push. It's likely that even where rotation leaves a trace, the trace is folded into the average that polarimetry reads as grain physics. One last thread is worth weaving in now, because it prevents a common misreading. Unusual polarization is not a synonym for artificial structure. It is a signpost for texture and coating at small scales. Think of it as a diagnostic more than a verdict. Observation suggests that negative branches of this kind appear in surveys of dust-rich comas when the grains carry frost or complex microstructure. It's likely that the interstellar origin of this traveller adds a little intrigue to the story, but it does not rewrite the physics of how light interacts with rough, icy particles as fresh data arrive after the bright interval near the sun. The best uses of polarimetry will be comparison same angles where possible, same filters, and clean overlays of before and after. If the curve softens a little while water rises, that strengthens the case for changing coatings rather than a new population of grains arriving from nowhere. If the curve holds firm across angles and time, that tells us the initial grain mix was robust and stable. Either way, the conclusion remains a calm one. Dust and ice are telling us about texture, not technology. Hold a small, steady image as we close a rounded glow with a slightly brighter face toward the sun, and within that glow countless icy grains turning sunlight into gentle, polarized whispers. Those whispers point back to texture and temperature, which is where the safest meanings live. With those meanings in hand, we can widen our view from physics to framing how distance and measured messaging keep this encounter untroubled. In the next chapter, we'll rest in that wider view and let safety and purpose carry the tone. Chapter 13, Calm Distances. Steady Science. We can take an easy breath here, because this visitor keeps a wide berth, and our role is simply to watch with care. Public attention often begins with the question of risk, but the sky has been patient and clear on that point. Observation suggests the object's path stays far from Earth and keeps to a clean, unbound curve that will carry it away again when this passage ends. It's likely that this is the rare kind of encounter where safety is a settled backdrop, letting curiosity lead in front. With distance assured, the work becomes craft planning exposures, aligning instruments, and building a record worth returning to long after the glow has faded. A steady message from agencies helps set the tone. When updates emphasize opportunity rather than hazard, they invite us to lean into the details without a drumbeat underneath. Observation suggests that communication has followed the data, a compact nucleus wrapped in an active coma, gas and dust behaving in ways that match sunlight on cold material, and a trajectory that does not need a hidden push to be explained. It's likely that such framing lowers the temperature of speculation while keeping the door open to wonder. In that calm, you notice the quiet choreography of a coordinated campaign. Ground surveys keep the beat of motion, logging positions and changes in brightness as viewing conditions evolve. Space telescopes add spectra and high-resolution images that isolate faint signatures and resolve the sunward haze. Observation suggests that roles were chosen to complement one another, wide fields to catch the extended carbon dioxide envelope, deeper looks to find water in both grains and vapor. It's likely that repeating those roles after reappearance will turn snapshots into a film where change is easy to see. Distance is not just safety, it is clarity. A large gap smooths out the daily churn of near-space weather and reduces the risk that local effects will masquerade as signals from the object itself. Observation suggests that the coma's smoothness and sunward enhancement have held across angles in a way that favours ordinary scattering. It's likely that the broad picture will persist even as details sharpen, a forward-leaning brightening where grains survive and scatter, and a rounded halo where many small sources overlap. The pace of science becomes visible when you listen closely. Teams write down what settings they used, how they calibrated, and what they compared against. Then they do it again under similar conditions. Observation suggests this discipline is already paying off, with independent instruments agreeing that carbon dioxide led early, while water showed up as both ice and vapor. It's likely that this agreement will stay intact as the angles change. Turning earlier hints into firmer statements about layering and porosity near the surface. Another comfort is how motion and chemistry keep telling the same story. The path fits gravity without needing a persistent extra term. The composition fits evaporating ices without needing an unfamiliar ingredient. Observation suggests that even the odd pieces and unusually deep negative polarization at small phase angles and a gentle sunward brightening find their place in models of icy, aggregated grains seen under changing light. It's likely that as more phase angles are sampled, the polarization curve will relax toward familiar shapes. The way a theme variation suite returns to its core melody. Patience is not passive in a case like this. It's a method that protects meaning by letting the pause near the sun happen without anxiety. Observers line up the same filters, the same gratings, the same cadence on the other side. Observation suggests this is exactly the plan: repeatable spectra to track the balance of gases, repeatable imaging to track the profile of the halo, and repeatable polarimetry to watch the grain story evolve. It's likely that the clearest insights will come not from any single frame, but from overlays where before and after share the same scale. Skepticism has a home in steady science, and it helps here. If a claim leans on a surprise, the simplest test is to ask whether the surprise survives new angles, new times, and new instruments. Observation suggests that features described so far do survive, but they survive as ordinary physics would have them survive stronger under forward scattering, softer at larger phase angles, consistent with many small sources rather than dominated by a few flamboyant jets. It's likely that the reappearance period will continue that pattern of consistency, narrowing the room for interpretations that require something beyond sunlight and ice. Safety and purpose are close companions. Knowing there is no hazard frees the mind to care about how the coma breathes, how heat moves inward, and how grain coatings change as water wakes into a larger role. Observations suggest that follow-up will press gently on each of these, whether the carbon dioxide envelope remains broad, whether the water signal strengthens as expected, and whether the polarization dip softens in step. It's likely that each result will be incremental, and that the elegance will lie in how well the pieces fit. If you want a simple image to carry out of this chapter, let it be a carefully kept notebook rather than a blinking headline. Each page holds a time, an angle, an instrument, and a result. When pages line up and the handwriting matches, confidence grows without fanfare. Observation suggests that this is the quality of record we are building now measured. Consistent and patient. It's likely that such a record will still be teaching when memories of the public moment have faded. With distance, cadence, and communication settled, we can let our attention slip beneath the surface for a while. What we see in the light today is the echo of choices made in a birth disk long ago. In the next chapter, we'll follow those choices, exploring how a carbon dioxide forward mix might arise and why a modest crust could shape what we see without changing who this traveller is. Chapter 14, How Such a Recipe Forms Disk Chemistry Ideas. We'll take this slowly, knowing the object remains a distant study. While we look for gentle causes behind the chemistry, we see a composition is a history in shorthand. What leaves the surface under sunlight reflects where the body formed, how it was assembled, and how its skin has aged in space. Observation suggests that early spectra favoured carbon dioxide over water at the distances sampled. With water present as both icy grains and vapour, it's likely that this balance is a snapshot of a layered system's official zones responding quickly to light, deeper reservoirs waking later, and textures in between that guide what escapes first. One straightforward path to such a balance begins at birth. Protoplanetary disks host temperature bands where different ices condense, often described as ice lines. In cooler zones, carbon dioxide can freeze efficiently while water remains bound deeper, or in textures that release it less readily at the temperatures we're seeing now. Observations suggest the coma's broad, carbon dioxide-rich envelope was already in place before the pause, which is consistent with an inventory that frees that volatile early. It's likely that as the season matures, water will strengthen, not because the recipe has changed, but because deeper layers begin to speak. Here is a calm what-if to hold with an open hand. What if the object formed near a carbon dioxide ice line, baking a carbon dioxide forward signature into its outer layers? Even if that is true, it remains a natural outcome of disk chemistry and temperature structure, not a sign of anything crafted. The reassurance belongs beside the idea, so the thought stays grounded. Another path to the same early balance comes from skin, not core. Over time, radiation and earlier heating can sinter the outermost grains into a low permeability crust. Such a crust can act like a valve that slows water's escape more than carbon dioxide's, at least until heat works through or fractures open. Observation suggests that a smooth coma and a gentle sunward brightening fit many small sources rather than a few sharp vents, which leaves ample room for surface gating to play a role without making itself dramatic. It's likely that if a crust is present, post-pause spectra will show water's share rising as the valve loosens. A second what-if fits here as a companion to the first what-if, a modest, low permeability crust has been holding water back, making carbon dioxide seem stronger than it is in the bulk. Even if that holds, it simply describes a surface texture doing what surfaces do when they age. It does not imply hidden design. The reassurance sits immediately after the idea, where it belongs. Dust and ice are honest witnesses to these processes. Coatings of water ice can freshen as deeper layers contribute, then thin as grains drift and sublimate. Observation suggests an unusually deep negative polarization at small phase angles, a sign that icy, aggregated grains play a role in scattering. It's likely that if coatings change with a rising water contribution, the polarization curve will soften at some angles and brighten a little at others. Such an evolution would be a quiet confirmation that the skin is changing while the deeper recipe remains steady. Kinematics can add context without overruling chemistry. Some analyses note that the inbound motion may align statistically with older stellar populations in the galaxy. If the body formed in an environment with a slightly different radiation climate or mixing history, its outer layers could carry that fingerprint. Observations suggest that motion and composition are in harmony rather than tension, an unbound path that needs no extra force, and a volatile mix that follows sunlight's lead. It's likely that provenance will remain a probability statement, while chemistry remains our most immediate translator of formation conditions. The absence of strong jets helps keep interpretations uncluttered, where a few dominant vents can imprint narrow structures and time-variable pushes. A balanced field of small sources averages into steadiness. Observations suggest that steadiness suits both the dynamics and the radiative signatures we've measured so far. It's likely that even as water strengthens, the coma will remain smooth, because more contributors will join rather than a small set taking over. That smoothness lets us treat changes in composition as genuine thermal evolution, rather than as the blinking of a handful of torches. Laboratory and modelling work give these ideas a place to rest. Ices mixed with dust do not act like pure slabs. They are porous, layered, and shot through with micropaths that can open or close with temperature. Observations suggest that the early dominance of carbon dioxide could arise from those micropaths favouring one molecule's escape over another's until warmth shifts the balance. It's likely that as the reappearance window plays out, production estimates will converge on a pattern. You can state simply, carbon dioxide steady or tapering gently, water rising to a more equal share as depth is warmed. If we return to the sunward feature with chemistry in mind, its calm meaning holds forward scattering brightens the lit side, and grain survival time set how far that brightening extends. A surface that adds more water over time can tilt the grain population toward frostier particles that live a bit longer before they fade. Observation suggests that the enhancement has been modest and aligned with the sun's direction rather than spear-like. It's likely that the post-pause profile will broaden slightly or shift its peak subtly if coatings evolve. In the same ordinary way dust physics predicts, there is satisfaction in how these pieces fit without strain. Birth conditions can explain a carbon dioxide forward start. Surface history can explain a valve that eases with warmth. Grain physics can explain polarization and profile changes as coatings evolve. Observation suggests that every one of these lines has a test ready at hand. Repeat the spectra, repeat the polarimetry, repeat the imaging at similar angles and let small differences carry meaning. It's likely that the combined picture will read as a single, coherent page rather than as a collage. If you want a single image to take from this chapter, let it be a quiet cross-section, a thin skin with pathways that open under heat, a shallow layer where carbon dioxide is eager to leave, and deeper seams where water waits its turn. The light we read is the sum of those layers speaking in order. That order is not a surprise. It is the way cold materials greet sunlight when the season turns their way. With chemistry's origin story in hand, we're ready to return to the ledger of measurements and see how new observations after reappearance tighten the estimates and settle the last loose edges. In the next chapter, we'll narrow ranges, test for tiny pushes again, and let a longer arc turn hints into clear statements. Chapter 15, Back in View, Tightening the Estimates. We'll ease back into the view, knowing the traveller remains far and the record simply continues where we set it down. When the line of sight clears after that bright interval near the sun, nothing dramatic is required. We return to familiar instruments, familiar settings, and familiar comparisons. Observations suggest the pre-pause pages already formed a steady baseline, a clean, gravity-guided path, a smooth coma with a sun-facing brightening, and spectra where carbon dioxide held the early lead, while water appeared as both ice and vapour. It's likely that the first task now is to replay those pages under nearly the same angles and cadence, so that the differences ring true. Astrometry is the quiet cornerstone of this phase. Observers place the object against the star field and let time do the sharpening. With a longer arc, fits tighten, and tiny drifts that once hid within nightly scatter can either resolve into a consistent term or dissolve into chance. Observation suggests the path to date does not require a persistent non-gravitational push. It's likely that the extended arc after reappearance will keep that answer calm, or reveal only a very gentle term consistent with venting that cancels over a rotation. Either outcome leads the same direction, ordinary comet physics with gravity telling most of the story. The second cornerstone is repetition. We take the same spectra and the same polarimetry again, as close as we can to earlier geometries. That sameness is not a limitation. It is the instrument that isolates change. Observation suggests that if water's role has strengthened with deeper warming, the signals will rise in the same channels where they were modest before. It's likely that a subtle shift in the balance will unwind through matched plots rather than single frames. Carbon dioxide steady or tapering gently, water lines brightening, trace species adjusting in step with temperature and depth. Imaging completes the trio. Earlier, the Comet's profile was smooth and forward-leaning, a modest brightening where sunlight falls, and a rounded glow where grains overlap. We look now for small, systematic adjustments to that profile. If icy grains survive a little longer as water contributes more, the sun-facing thickening can broaden, not as a spear, but as a softening of the gradient. Observations suggest that the earlier negative polarization branch at small phase angles pointed to icy, aggregated grains. It's likely that fresh coatings and evolving sizes will nudge that curve toward a slightly different shape at some angles, while leaving the overall appearance serene. This is also the moment to test earlier what-ifs without noise. One idea was that a low-permeability crust could have throttled water during the first looks, making carbon dioxide appear stronger than the bulk mixture. If a crust loosened during the bright interval, water lines should step forward now. Observations suggest that a careful before and after in the same pass bands can separate real change from angle tricks. It's likely that any measured rise will be gentle, a reminder that porous ice wakes in layers and speaks in gradual phrases. Mass and size estimates live downstream of all this. No one image will pin the nucleus with precision while the coma carries the light, but a chain of consistent measurements can push the brackets inwards. Photometry feeds models of dust production. Spectra feed production rates for gases. Astrometry feeds limits on any net shove. Observations suggest that these threads, woven together, narrow the plausible range for nucleus size and bulk properties without claiming more than the data allow. It's likely that refinements will arrive as small steps, the kind that reward patience rather than spectacle. The multi-vantage approach keeps its value here. Views from another platform or at a shifted phase angle provide cross-checks on scattering and structure, when Mars-side or distant perspectives echo Earth's results after accounting for geometry. Confidence grows that we are tracking the object rather than the angle. Observations suggest that earlier windows delivered that kind of complement. It's likely the reappearance sequence will preserve the habit, the same glow described in different lights. The same physics travelling across viewpoints. You might wonder whether any late surprise could still swing the interpretation. Science leaves that door ajar by design, but it also asks for evidence that not only stands alone but stands across methods. A claim about an unusual force would have to appear in the orbit fits and resist the averaging effects of a rotation. A claim about a novel substance would have to persist in spectra, taken by instruments with different sensitivities. Observation suggests that the convergences we have keep holding a gravity-ruled path, a volatile mix in familiar proportions that evolve with heat, and a dust population whose optical behaviour sits inside comet dust models. It's likely that late data will add detail rather than a new plot. Calibration is the quiet hero of this act. Teams revisit standard stars, check wavelength solutions, and reproduce exposure times so that a small change belongs to the object and not to the pipeline. This may read like housekeeping, but it is where trust lives. Observation suggests that earlier agreements between independent platforms came from this discipline. It's likely that the same care will turn reappearance into a smooth splice. A joint so clean you can forget it is there. If you want a gentle image for this moment, picture two transparent pages aligned on a light table, the earlier page and the new one. Lines and curves sit on top of each other, and where they diverge, they do so by millimeters rather than broad strokes. Those millimeters are meaning they tell you that water is rising here, that polarization softens there, that the sun-facing haze spreads a little wider under the same angle. Observations suggest that this is the scale at which the object speaks now. It's likely that listening at this scale will give us the truest reading of layers, boris, and path. None of this requires speed. The object remains a distant guest. Generous with time, we are allowed to measure, compare, and measure again. We are allowed to say that a small term is consistent with zero, and to let that be enough for a season. Observation suggests that careful repetition is the most powerful step left. It's likely that, taken together, those repetitions will let us close the ledger with lines that fit cleanly. Carry that calm forward. In the next chapter, we gather what the record now supports and let the best evidence answer the question that brought us here, with a tone as quiet as the traveller itself. Chapter 16, What the Best Evidence Says, a Quiet Conclusion. We can rest our shoulders here, because the record is long enough and the visitor has behaved with steady grace. A conclusion in science is not a drum roll. It is the place where independent lines meet and stay together. Observation suggests those lines have been pointing the same way. All along, a compact nucleus shrouded by a smooth, forward-leaning coma, outgassing that follows sunlight, a composition where carbon dioxide led early and water rose as warmth sank deeper, and a trajectory explained by gravity without a persistent extra shove. It's likely that the later additions, fresh spectra, longer arcs, new angles have done what addition should do. They have refined the picture rather than rewritten it. Start with motion. Because motion sets the tone, a traveller that follows a clean hyperbolic arc while measurements tighten is telling you that internal forces are either modest or balanced. Observation suggests the fits do not require a sustained thrust. It's likely that many small vents averaging to stillness describe the situation better than any single active source would. That reading is not an evasion. It is what the sky gives when countless minor breaths pull equally in different directions. Composition carries the second theme. The early spectrum favoured carbon dioxide, while water showed up in both grains and vapour. After the bright interval, water strengthened, and the balance eased toward what you expect when heat reaches a little deeper. Observation suggests that this evolution can be explained by two natural paths that may both contribute an inventory set near a carbon dioxide-friendly ice line and a surface that acted like a gentle valve until warmth loosened it. It's likely that the exact share of each path will remain a matter of weights rather than absolutes, and the science is comfortable with that. Light scattering ties the look of the coma to the materials themselves. The deep negative polarization branch at small phase angles sounded striking, yet it read as icy, aggregated grains when set beside the rest of the data. Observations suggest that as angles shifted and coatings evolved, the curve responded in step, softening where models anticipated and holding firm where grain families stayed constant. It's likely that the sun-facing brightening behaved the same way, changing by degree with phase angle and grain survival times, never once demanding a mechanism beyond sunlight and texture. Claims that lean toward artifice have had their chance to meet this record. A non-natural origin would ask for signatures that survive across instruments and geometry, a push that does not average away, a spectral imprint that resists ordinary chemistry, a timing that ignores the day-night rhythm of a rotating, sunlit surface. Observation suggests these signatures did not appear. It's likely that what felt unusual at first polarization depth, sunward enhancement, was the newness of an interstellar visitor wearing familiar physics, not a sign of intention. Safety sits gently at the edge of all this. The path has remained far from Earth, and the encounter has been a study, not a test. That distance allowed the cadence we chose planned exposures, careful repeats, comparisons that honoured earlier settings. Observation suggests that this discipline is why the pieces interlock so cleanly now. It's likely that the most useful legacy of this passage will be the shared method as much as the single object a model of how to watch. Across platforms and seasons, without leaning on drama, there is still room for questions that live beyond the immediate visit. Provenance will retain its probabilities, a motion that may align with older stellar populations, a surface that carries hints of a long interstellar cruise. Observations suggest those questions can be explored without altering the present reading. It's likely that each new interstellar object will add its own variations, and that the next one will meet a community practiced at listening with patience. So what, in the end, do we say when asked if we uncovered alien technology in this traveller? We say what the shared evidence supports in calm words. Observations suggest a natural, volatile, rich body behaving as sunlight and porous ice predict. It's likely that this answer feels smaller than the question, but it is sturdier. It lets curiosity keep breathing without turning wonder into worry. It also leaves the door open for future visitors to surprise us, because the standard we used here, convergence across methods, will serve just as well if the sky ever offers something genuinely out of family. I hope you can hold a single scene as we close the circle. A distant glow with a slightly brighter face toward the sun, a curve that does not close, written cleanly by gravity, a handful of spectra that show carbon dioxide first and water later, and a polarimetric trace that settles into the shapes grain physics draws. Observation suggests that this is enough to answer the question softly. It's likely that the truest part of the answer is the method itself, which is how we will meet the next visitor and the next. Let's keep that method close. In the final passage, we'll gather the thread of feeling curiosity, patience, and the steady comfort of good measurements, and set it down as a gentle farewell. I'm content to end on one real detail. no persistent shove beyond gravity showed up. Even as the gas mix evolved, from that calm centre, everything else falls into place. Observations suggest a compact nucleus wrapped in a smooth, sun-facing glow. Carbon dioxide spoke early. Water joined more clearly as warmth sank a little deeper. Polarization dipped in a way that icy, aggregated grains can explain. The path stayed the path, an open curve written by the sun's pull with activity that looked balanced enough to cancel its own small tugs. Nothing in those lines demands a special engine. They point to dust, ice, sunlight, and time, working together with the patience we know. The pleasure of this visit is how the pieces agreed. Imaging favoured a gentle brightening toward the sun, not a spear, but a gradual thickening shaped by forward scattering and grain survival. Spectra favoured a wide envelope of carbon dioxide with water present as both vapour and ice, shifting by degrees after the bright interval. Polarimetry favoured rough, frosted particles that deepen the negative branch at small phase angles and relax at others. Astrometry favoured a gravity-only arc, with any extra pushes too small or too balanced to stand out. Each method speaks a different dialect, yet they told the same story. It's likely the remaining refinements will arrive as small steps, tighter limits on any subtle acceleration, cleaner production rates for gases, and a clearer map of how coatings on grains change with distance and time. Those steps are not the end of wonder. They are how wonder matures. They keep curiosity honest without forcing it toward a grand answer. It doesn't need. If a future traveller breaks the mould, this quiet standard will make that difference plain. Until then, the best evidence here describes a natural, volatile, rich body behaving as physics says it should. I'll close the loop with one anchor. You can hold a Foucault pendulum in a quiet hall after hours. Its slow arc, proving the ground beneath your feet is turning. No fanfare, just truth unfolding with time. The visitor's record feels like that swing after swing, page after page. The same direction affirmed by independent eyes, the same steady handwriting of gravity, the same measured rise of water as heat works inward. You can leave these findings on a shelf and return later. They will still be there, still aligned, still enough. If you'd like a calm companion the next time a distant traveller appears, I'd be glad to keep watch with you.